Calculation and homemade construction of a toroidal transformer. The toroidal transformers are inductors in donut shape, are very used in high-power amplifiers. Experts in this fine art, like the Philippines and the Indonesians, they use toroidal transformers to feed the amplifiers of their gigantic portable soundboxes. An example of this is using the annual competition Dinagyang Sound Showdown in Iloilo, Philippines. Now we will see a practical and easy way to make a homemade good performance toroidal transformers. Transformer theory. The transformer comprises a primary winding and a secondary winding, both coiled to a core and are isolated from each other. Can be designed to increase or decrease the voltage or also use it to isolate the voltage public network. The primary winding receives the voltage of the public network, either 120 or 220 volts AC, depending on the country, while the secondary winding delivers the output voltage of the transformer. The secondary winding is driven by the magnetic field, which is generated by the primary winding, which is induced by the core. The potency transfer between the primary winding and the secondary winding is magnetically performed through the core and air. Advantage of a toroidal transformer. In the classical transformer's cores armed with H-shaped plates and I-plates, the flow of the magnetic fields has to turn around to follow the profile forming plates, forcing the electrons to leave the junction of the plate's A's with the plate's I, generating a magnetic flux leakage. Meanwhile, in toroidal transformers, the magnetic flux runs through the core, always rotating in the direction of its circumference, meaning in the same direction of its lamination. The fact that the toroidal core is formed of a long strip of sheet spirally wound makes them more efficient. Another great advantage is that to achieve the same inductance equivalent of a classic transformer, a toroidal requires fewer turns and can be made in a smaller size. Once built, you'll notice that the toroidal generates less heat than a conventional transformer, allowing us to use thinner wire and a smaller core. Materials. Core. The core of a toroidal transformer is made of long iron silicon sheets winding in a spiral. You can get them plated and grab the amount needed to achieve the desired core. In this case, we use a recycled core. Magnet wire. The magnet wire is an isolated copper wire with a coating of a dielectric varnish. You can get it in many gauges. In some places, it's sold by weight and others by meters. Polyester resin. It is a synthetic fiber derived mainly from oil and coal. It is very used in the industry today, for example in the automobile industry. Cardboard box. The core must be wrapped with a thick cardboard at least 2 mm. This greatly improves the core inductance and it is imperative. Copper plate. Must be about 20 gauge. Of this sheet, cut off a plate that covers the circumference of the core and will serve as grounding. Rubber coated cable. Input and output cables transformer are coated rubber. We recommend using heavy gauge. Adhesive tapes of different types. The adhesive tapes we are using are masking tape to cover the core and windings and transparent tape for the final look. Neoprene heat shrink tubing. Allows you to electrically isolate the binding of wire with cable. Tools. Shuttle. The shuttle is a thin piece of wood used to grab the wire longitudinally. We recommend make several of these 50 cm long and width according to the different sizes of cores. Scalpel. It's used to cut the cardboard, wire, stripping, etc. Scissors. They serve to cover the cardboard and copper wire. Tweezers or pliers. Used to braid cable with wire. Soldering iron and welding. Used to weld the cables with the wire. Cable stripper. As its name implies, is used to peel the rubber of cables. Sandpaper is used to remove the dielectric coating of the ends of the magnet wire in order to be welded. How to calculate the core? From knowing the potency of the device to be fed, you can always calculate the core size. For this, we must calculate the square root of the power delivered by the machine, in this case 1200 watts amplified, and we will find the area of the cord. The square root of 1200 equals 34.6 cm squared. The cord to get should always be above the measuring obtained in square centimeters. In this case, we get a cord with an area of 35 cm squared. How to find the area of a nucleus? Very easy. We measure the outside diameter, the inside diameter, and its height. To the external diameter, we subtracted the inner diameter, the result is multiplied by the height and divided in 2. In this case, we have a core of 18 cm of external diameter, 8 cm of inner diameter, and a height of 7 cm. 18 minus 8 equals a 10. 10 multiplied by 7 equals 70. 70 divided in 2 equals to 35 cm squared, which is the area of the core. A core with an area of 35 cm squared is capable of supporting up to 1225 watts. Isolation of the core. Now we must prepare the core. The core should be adjusted and then sealed to the top and bottom with polyester resin, the same one used in the fiberglass. We apply a few drops of MEG or activation for hardening the resin. Mix the resin and the activator until you obtain a uniform composition. Then applies the resin liberally to the spiral of the core, bonding the turns of the plating. When the resin is completely dry, the core is flipped and the resin is applied on the other side. This process is done to avoid the plate which forms the core rub with each other because of the vibration generated, which ultimately becomes heat. Let's now proceed to make the formwork for the core using a cardboard box. We trace twice the circumference internal and external of the core on the cardboard. We cut both circles. We cut a pair of cardboard strips that measure the height of the toroid for coating on the external and internal contour, with long enough to turn around the outside and the inside of the toroidal core. The inner cardboard strip is placed, and we secure it with masking tape. Now the other cardboard strip is placed. This one is also secured with masking tape. We place one of the circles on the top of the core. This should fit perfectly between the external and internal strips. We shall use quite a lot of masking tape in order that there's no space where the core can touch with the wire to roll up later. We turn the core and put the other cardboard circle. We assure and we seal well with masking tape. It is important to emphasize that the more thicker the isolation cardboard and masking tape are, more faster it will turn off the series circuit, and therefore the transformer will have a better performance. Calculation of wire turns of the primary winding. As a general rule applied, we will use the constant 42. This one is divided into the core area, resulting in the number of turns per bolt that we're given in the core. 18 cm of external diameter minus 8 cm of internal diameter equals 10 cm. Then multiplied by 7 cm tall equals 70. 70 divided 2 equals 35 square centimeters, equivalent to the core area. Now let's apply the formula with the constant 42. 42 divided in 35 equals 1.2 turns per bolt. Now we multiplied 1.2 turns per bolt by 120 volts of the public network of our country, and we will get 144 turns for the primary winding. Calculation of wire in meters. To calculate the number of meters of wire using 144 turns, we measure the length of a turn of a wire, in this case are 25 centimeters. Multiply 25 centimeters by 144 turns. It equals 3600 centimeters. Now, 3600 divided in 100 equals 36 meters of wire. Calculating the size of the primary winding wire. The wire gauge is obtained by dividing the output of the amplifier, in this case is 1200 watts, into the number of volts of the public network. Remember the Watt's law. Output divided volts equals amperes. 1200 divided 120 equals 10 amperes. If your country public network delivers a voltage of 220 volts, 1200 divided 220 equals 5.4 amperes. Now we check the American wire gauge table that has the relations between the wire gauge and amperes. In our case, 10 amps equivalent to 13 gauge. Remember that the toroidal transformer is more efficient, therefore we can use a caliber below without fear of overheating. So we'll use a 14 gauge wire for the primary winding. If your country public network delivers a voltage of 220 volts, then the gauge of the wire of the primary winding will be 16 or 17. Calculating the wire in grams. If in your city sell wire by weight, that is in grams, pounds, and kilograms. You must calculate the weight in grams of the primary winding. Stretch and cut an exact meter of wire gauge to use. The wire is weighted on a precision scale, and the number should be multiplied by the amount of meters required. In this case, we have a meter of wire gauge 14, which weighs 18.6 grams. Like we need 36 meters, 18.6 gram multiplied by 36 meter equals 669.62 wire to the primary winding. This amount can be approximated to 670 grams. Winding turns for the primary winding. Having already the wire of the primary winding, we should sand one of the end to remove the dielectric varnish. This is done so the solder will weld right to the wire. Now, we cross the tip what we just sent through the small hole at one of the ends of the launcher and then begin to wind the wire. As the launcher measures 50 centimeters long, every complete turn will be a meter of wire. As we need 36 meters, give 36 full turns. At the end of the wire, you need to sand about centimeter. We thin the wire. We take a piece of rubber side wire and we remove 1 centimeter of the rubber. We thin the tip of wire with abundant welding and join wire with cable. To achieve perfect isolation, cover union with heat shrinkable spaghetti. The wire with cable union is placed in the center of the core. We set it with masking tape. Then, we begin to wind the wire passing the launcher through the center of the core. This should be done in an orderly manner and trying not to mount a turn on the other. The turns of wire must be distributed proportionally on the ground through the cord. Also, should be kept very tight because later there will be vibrations on the wire. When we take a 30% turns of wire needed, we do a test connecting the series circuit at the ends of the wire. We will see the bulb full turns on. This shows that it's still in short the lack of more turns of wire. We continue winding wire given to maintain order and tension. Reaching the half winding to give, we do another test with the series circuit. We know that the intensity of the bulb has down to the half. We wind the turns of wire missing. When we finish winding the calculated turns for the primary winding, we check with the multimeter if there's continuity in the wire. Check the series circuit and we see that the bulb turns up in the joint in the tips, causing a short. We reconnect the series circuit at two ends of wire and we see that even though the multimeter measures continuity, the bulb doesn't turn on. This means that the primary winding is ready. At the end of the wire, we weld a piece of cable as we put at the tip at the beginning. And we isolate the union with a piece of heat shrink. Top off the primary winding. Adjust the wire very tight. We use masking tape to keep the end of the wire in place. What to do when the series circuit doesn't turn off? When the series circuit doesn't turn off, indicates lack of turns of wire and that the calculations were wrong or that the cord is of bad quality. We must continue winding wire until the series circuit turns off completely. Now that turn off the series circuit, we count all given turns of wire, obtaining a total of 144 turns. Another way to find the number of turns per bolt consists in dividing the given turns in the primary winding with the voltage of the public network. 144 turns given divided 120 volts equals 1.2 turns per bolt. Isolation of primary winding. Now that we were sure to have a perfect primary winding, we should isolate covering it with thin cardboard or press pump paper. First, we cover the inside of the transformer. Now we cover the outside. We cover the top with a ring of the same material and secure it with abundant masking tape. We rotate the transformer. And likewise cover it with a hoop of press pump paper and plenty of masking tape. Tighten as much as possible. Adjust it with tape the wire of the primary winding to avoid possible vibrations. The transformer should be covered with abundant masking tape. Calculating secondary winding. Our transformer must deliver an output of 1200 watts to winding 60 plus 60 volts. Also, we'll have an additional 12 volt winding and another 50 volt AC. To find the number of turns of the secondary winding is multiply the average voltage, the half of the total voltage, by the number of turns per volt. 60 volts multiplied by 1.2 turns per volt equals to 72 turns of wire in double for each secondary winding. Remember that you must wrap the two wires equals at the same time. Calculating the gauge of the wire of the secondary winding. The gauge of the wire of the secondary winding is calculated according to the type and number of transistors which carries the amplifier. For example, if we use 12 transistor 2SC5200, each consumes 1.3 amps to obtain a total of 15.6 amps. The gauge of the wire endured over 15.6 amperes is 11 gauge. But having in count that a toroidal to allow using a lower gauge, we use a 12 gauge wire according to the American wire gauge table. Calculation of wire in meters. To know the necessary meters for wire for the secondary winding, again we measure the length of a turn of a wire, because the primary winding increases the core thickness. 27 cm multiplied by 72, that is the number of turns of the secondary winding, equals 1944 cm. This result is divided into 100, and get 19.4 meters double wire for the secondary winding. Then, we bind 39 meters of 12 gauge wire. Calculating the wire in grams. For knowing the weight in grams of the secondary winding wire, weight 1 meter of gauge 12 wire weighs 26 grams. This amount is multiplied by the required meters. 26 grams multiplied by 38.8 meters equals 1008 grams. Copper shielding. Now we place a copper shield that will be the ground. We measure the circumference of the core. We cut a strip of copper the same length as the circumference of the core, 2 cm less than the height of the core. In this case, it is 60 cm by 5 cm. At one end of the copper strip, a piece of wire is welded. And then cover it with cardboard or pressman paper, and we secure it with masking tape. The strip of copper is placed around the transformer and secured with masking tape. This copper shield serves to prevent possible magnetism leakage which might interfere with the circuits, especially if there are preamps or small signal circuits. Winding the secondary coil. We now proceed to rule up the secondary winding. As the secondary winding is dual or symmetrical, this means having a central point or center tap. We grab the wire in double. So, first I roll the amount of meters of wire calculated before on the launcher, being the two wires at the same time. Then we hold the two ends of the two wires inside the core and stick on with masking tape. The wire is wound on the toroid orderly and tight, considering that the wires do not get wimped with each other. Upon completion of the secondary winding, attach the tip of the beginning of one of the wires with the end type of the another wire to form thereby the central tap. Be careful not to attach the ends of the same wire. To check this, use the help of a multimeter at a continuity scale. The multimeter shows continuity measuring the tips of the same cable. So the two ends that do not mark continuity are the ones to be joined. The next test is made with a multimeter at AC voltage scale. By measuring between tap and each of the ends of the wire, the voltage should be fully symmetric. Then measure between the two ends and should measure twice the voltage. It is imperative to check the previous compromission of the central tap using always the series circuit. This is also done for your personal safety. We can see that the voltage gave us 62 volts and we had calculated for 60 volts. We measured the voltage public network and found that the cause is because the voltage of the public network is a little higher. Having done this, we proceed to weld the junction of the central tap. We should sand the wire's ends very well to obtain good adhesion of the tin. We gimp both ends to form the central tap, adjusting them strongly. Retaining the tips with plenty of welding wire. We will good gauge wires in each of the wire ends. Use a different color cable for the central tap. Cover all union with some heat shrinkable pieces. We can cover the secondary winding with transparent tape to give an elegant look to our transformer. Additional winding of 12 volt AC. Now we make an additional winding 12 volt and 1 amp for powering 2 cooler fan. To To calculate the wire gauge of number of turns, we use the same formula like this. 42 divided 35 centimeters squares equals 1.2 turns per bolt. 1.2 times 12 volts equals 14.4 turns of wire, that approaching 50 laps. The gauge of the wire is determined from knowing the consumption of the cooler fans. In this case, we will use two cooler fans of 0.4 amps, which together consume 0.8 amps. For this reason, we use a wire carrying 1 amp according to the American wire gauge table. It's the 23 gauge. We wind the cable as it has done before and finish off with welding rubber coated wire in each of the wire ends. Cover it with heat shrink tape and cover it with clear tape. Use the multimeter to check our additional winding. A transformer can have more than one secondary winding and additional windings. Our transformer has two secondary windings 60 plus 60 volts AC. We also add an additional winding 12 volt 1 amp that serves to feed the cooler fans. And yet another winding of 15 volts that we would use to regulate and feed the speaker protectors. At the end, we gave a finish with transparent tape keeping the wire inside. We truly believe that this is the easiest, economic and reliable way to make toroidal transformer, because will allow you to assemble and begin to set up of higher power devices without you being an expert on the subject. It's easy. Success! Watch our suggested videos. We invite you to subscribe to our YouTube channel. Go to the tool button and check the box Send Me Updates. Join us on Facebook and follow us on Twitter. Visit our website construyesuvideorocola.com.